Assalamualaikum, how are you? Morning. Can you hear me? Okay, good. Okay. Okay, let's get started. Right, yesterday we have started discussing about solar cell, introduction to PV, um, operation of solar cell, and what else? Solar spectrum, a bit on history, IV curve, and how we determine short circuit current, open circuit voltage, fill factor, um, and finally the conversion efficiency of the solar cell. Right. So today we're going to move on to the next part. We're going to look at PV technologies available in the research phase and in the market. And then we're going to look at outside physics aspect. We're going to look into manufacturing, annual production. I'm just going to give you some perspective of what's going on in the industry now. It's going to be useful to you, especially when you want to go for your internship. If you decide to go to solar cell companies, we have plenty of solar cell companies around us in Bayalapas, in Prai, in Kulim. In fact, we also have in KL, in Johor, in Sarawak as well, and they are all top and giant companies in the world. So we are quite blessed in that sense. So that's why I decided to also include the manufacturing aspect of the solar cell, so that you have some ideas to talk about if you want to join solar cell manufacturers. In fact, if you talk about your seniors in terms of their internship, this batch this year, they are all together four of your seniors from applied physics, and one is medical physics, surprisingly. Okay, four of them are in solar companies doing their internship. Three of them are in JA Solar in Penang, Bayalpas, and one is in Jinko Solar, Prai. Okay, so they're all together four. Last batch, if you talk about internship in solar companies, they were six of them in Jinko Solar. So I think they're all together four from applied physics and two from engineering physics last year. Okay, so this year we have them in two companies, Jinko Solar and JA Solar, right? Okay, so let's move on. I'll give you more and more information on those topics as we go along, right? So when you talk about solar cells, they are all together three generations. So we call it three generations of PV technologies. We call it as Gen 1, Gen 2, and Gen 3, or some people call it first gen, second gen, and third gen. Um, Gen 1 is mainly on wafer-based solar cells. So they are monocrystalline silicon solar cells, and they are multicrystalline silicon solar cells. Right? Multi is also called polycrystalline, but generally they are called multicrystalline silicon solar cells if they are in wafer-based. But if they are in thin film based, which is second generation, they are, if you talk about silicon, then they are called polycrystalline rather than multicrystalline. I'm going to go through the diagram here, but let me just brief to you first. Second generation is all about thin film solar cells. So when we say it's thin films, then that means the materials that we use to form the absorber layer to do the light absorption is much lesser than the wafer base. So if you're talking about wafer base, the typical thickness is around 180 micron now in industry. If you talk about thin films, it's around 1 micron to 5 micron roughly in industry. And the third generation is for a thin film solar cell as well, but with higher efficiency compared to the second generation. So let's look at the diagram here. So the diagram here shows you the efficiency of all generations of solar cells with the cost related to the fabrication of the particular technology. All right. The first gen is notated, is given by the green oval there. Second gen is the yellow one. Third gen is the green one, the red one. Sorry. So if you look at the first generation is actually the first ever type of silicon, first ever type of solar cell ever made, which we discussed yesterday back in 1954, the first demonstration by Bell Lab, where 6% conversion efficiency of solar cells fabricated back then. So if you look at the conversion efficiency on the y-axis, the typical conversion efficiency of the first gen or wafer-based silicon solar cells, be it multi or monocrystalline, they are typically in the region of 18 to 24%, right? 18 to 24%, and this graph is is created a couple of years ago, quite a long time ago, right? And the conversion efficiency of the wafer-based solar cell is roughly about 18 to 24%. While the cost, if you notice, the cost is very high to fabricate the first gen solar cells back then. We're going to go through the cost curve later on, but briefly I can tell you 10 years ago when I did my master's back in 2010, the technology cost, we talked about it yesterday, USD per watt, the benchmark is USD per watt. The technology cost for crystalline silicon solar cell was around $3 per watt. So that means $3 per watt. Okay, so and this curve on the page now is on US dollars per square meter. So which is another dimension to translate the cost. But when we talk about USD per watt, or how much you need to spend to fabricate the solar cells over how much power can you extract from the solar cells, so it's roughly about $2 to $3 per watt. And now the cost for the crystalline silicon solar cell is only about 22 cents per watt. So dia dah turun about more than one order of magnitude, daripada $3 kepada about 20 plus cent as of 2019, right? As of 2019, we're going to go through later on. So back then, since the cost of the first generation silicon solar cells was too high and not really affordable, so scientists came out with another generation of solar cell, which is called second generation solar cells. And the motivation to have this second gen is to reduce the cost. But then if you reduce the cost, which is mainly done through reduced material consumption, which I said before, where crystalline silicon solar cell typically use around 180 micron, 200 micron of materials, whereas for thin film thin film solar cells, if you talk about thin film silicon, so it's roughly about 2 micron to 5 micron. So that's a huge reduction of material consumption. So logically, if you talk about this huge reduction of material consumption, we are actually reducing the cost as well. But then the problem is when you reduce the material consumption, you are actually reducing the volume of the material that we use for the interaction of light to material. So that means bila kita reduce material volume yang kita guna untuk solar cell, what is the impact? Kita discuss hari tu. What happens when we reduce the material consumption? If you reduce the thickness, what's going to happen to the light absorption? Boleh tulis kat sini ataupun nak cakap apa? What happens bila kita reduce volume or the thickness? What happens to the light absorption in the solar cell? Is it getting better or it gets worse? Better or worse? Anyone? Worse, yes, worse. Remember? Recall back my example dalam kelas yang pakai sponge tu. Kan? Masih ingat the sponge example? Thick one and thin one. Kalau kita pakai yang lebih nipis, apa jadi dekat absorption of water? Kurang kan? Because of the less volume. So the moment you go for lesser material, with the motivation to reduce the cost, we end up absorbing less light. So when we end up absorbing less light, we end up with lower conversion efficiency. So that's why you can see here the conversion efficiency of the second generation silicon solar cell reduces a little bit, and the typical conversion efficiency of the thin film is roughly around 8% to 15 to 20, 8 to 15% roughly. It really depends on which type of materials you use for your absorber. Okay, so that's the original motivation. So back then the motivation was to reduce the cost. So the second gen was created. So then time goes on, the scientists think that the conversion efficiency is not enough, and it's very hard to push the conversion efficiency of the second gen solar cells. So then the third generation was created. So it's based on thin film solar cells still, but then the motivation is to go to high efficiency sebab dia nak compensate balik lah efficiency loss due to the reduction of the material consumption. So then we have the third generation solar cells. So maksudnya you can see here, if you compare third generation and second generation, they are pretty much on the same cost roughly, but the conversion efficiency of the third gen is much higher than the efficiency of the second generation. Okay, right, this is the brief summary of each generation. So if you talk about first generation solar cells, it's mainly consists of monocrystalline silicon solar cells in the center here, and polycrystalline silicon solar cell, or we typically call it multicrystalline silicon solar cell, right? So they are both in first generation technology, right? They're already in heavily mass produced. They now dominates about 90% of the PV market. So this first generation technology. So if you look at the second generation, it's also in the mass production. Second generation is thin film solar cells. So they are like cadmium telluride that we discussed before in our presentation. They are also amorphous silicon solar cells. They are also copper, indium, gallium, selenide solar cell. They are also ZAT386, copper, zinc, tin sulfide solar cells. So this is among the second generation solar cells. Copper, zinc, tin sulfide, cadmium telluride, amorphous silicon, copper, indium, gallium selenide, right? So they are the second generation solar cells. They're also in mass production. In fact, we have First Solar in Kulim fabricating cadmium telluride solar cells, but we don't have any manufacturer in Malaysia doing CZTS, amorphous silicon, and CRGS. If you talk about the first generation, we have a lot of these companies in Malaysia. So in Penang alone, we have JA Solar doing mono and multi in Bayalpas, and we also have Jinko, one of the world top in Prai, doing mono and multi. We also have Panasonic Energy in Kulim doing mono. We also have Q Cells in Hanwal Q Cells in Cyberjaya doing mono and multi. We also have Longyi in Kuching Sarawak doing mono and multi. So we have all the top giants. I'm going to show you later on. We have all the top giants in Malaysia right now. Okay. If you talk about the third gen, for example, organic solar cells, perovskite solar cells, they are mainly in research phase. There are also some companies doing organic solar cells, mass production, like Konarka, Helios, I think Helios, or Heliotech doing third generation organic solar cells. But the volume is not a lot. Right, first generation solar cells. Let's have a look at the solar cell. In the previous page, we looked at the panel. The panel is what we call a plate that consists of a couple of solar cells, typically about 60 solar cell or 72 solar cells, or in fact 96 solar cells. Right? Okay, this is first generation. Mono on the left and multi or poly on the right. So monocrystalline is the single crystal we learned before last time when we started the class. Multicrystalline or polycrystalline composed of more than one crystals. You can see clearly the green boundaries by the dark blue here, light blue here, and they are in fact random in nature, so you can't really control the grain distribution, except you know that the grains are visible. The grains are typically centimeter in size. You can actually see the grains from your naked eyes. Okay, so in the industry, both of these are used with 180 micron thickness. So it's roughly about twice of our hair thickness. Okay, so in fact the thickness is going lower as we go along into the future. And if you look at if you're more interested to know about this, you can check out ITRPV. This is International Technology Roadmap for Photovoltaics. It's like a document which forecasts what's going to happen to the field in the next 5 years, 10 years. So in fact, if you talk about the thickness, so it's forecasted that the wafer thickness will go down to around 100 micron in the future. So why is it the case? There are so many reasons for that, right? So efficiency for this technology ranging from 18 to 25%. It lasts for 25 years. So the moment you purchase the technologies, you put it on the roof, so it will last for at least 25 years, guaranteed, right? It will show some minimal degradation over time. So that means it's going to degrade around 0 point something % over 1 year. So you're going to end up with some amount of degradation over the 25 years period. Okay. One cell, if you talk about one cell, okay, let me tell you a little bit more. One cell is roughly 6 inch by 6 inch. One cell yang square inch, dia punya dimension is roughly about 6 by 6 in mass production. Kalau dalam lab kita hanya pakai 2 inch, 3 inch. If you talk about no lab, kita pakai silicon 2 inch kan, kita pakai 2 inch yang bulat tu. So it's only about 2 inch or 5 cm. 5 cm. Kalau dalam lab lah, ni lab scale. So if you talk about mass production, it's 6 by 6. And in fact, industry is pushing for a larger wafer format. So they're gonna go for bigger and bigger over time. So in the next couple of years, we might see bigger and bigger panels delivering more and more power. Okay. Right, so let's go to the second generation. Second generation, the moment you say it's thin film is very thin. Typically it's about 1 to 5 micron, 1 to 8 micron. It really depends on the technologies. Waktu saya buat PhD hari tu, when I did it in UNSW, I work on second generation solar cells, which are based on polycrystalline silicon thin film on glass. So back then I work on this. So ada glass kat sini, glass. Then I have my polycrystalline silicon. So the thickness is only about 10 micron. 10 micron. Okay. So, and the polycrystalline silicon was originally deposited by electron beam evaporation process. We're going to go a little bit deeper when we talk about fabrication process next semester. So I evaporated the silicon in the form of amorphous silicon using electron beam evaporation 10 micron, and then the amorphous silicon was laser crystallized. So saya guna laser untuk scan the amorphous silicon and melt the amorphous silicon, and at the same time crystallize the amorphous silicon in the form of polycrystalline. So eventually I have a 10 micron thick polycrystalline silicon to be my silicon absorber, right? So the PN junction, kalau saya punya PhD PN junction was formed at the back. So ini yang saya cakap, apa, the junction is not necessarily on the front side, it can also be on the rear side. It depends on the technology that we fabricate. So in my case, a couple of years ago, my PhD was on rear junction polycrystalline silicon solar cell. So I have my P in the absorber, I have N my emitter. I also have a couple of cells using N as my absorber and P as my emitter. So contact semua duduk kat belakang. Contact N duduk kat belakang. Then I can also do a contact into the absorber area. So that means I need to etch. Saya kena korek area yang tengah tu. So then put a contact into the absorber area, and then some contacts into the emitter area, and then I can have my PN junction at the back. Everything is at the back, right? So let's go back to the second generation. When you say it's thin film, maksudnya the thickness is very thin. It's in the region of 1 to 10, 1 to 5, 1 to 8. It depends on material. So the whole idea is that when you go to thin film, it cannot stand on its own sebab dia terlalu thin. Kan? If you imagine kalau you ambil punya rambut, it's about 100 micron thick. You pegang rambut, it cannot stand on its own already, right? So it's already, dia dah bend kan sebab rambut lembut. So just imagine how do you make sure 10 micron, which is rambut slice another 10, to stand on its own. It cannot stand on its own. So therefore, the material, the absorber layer yang you pakai ni, doesn't matter is polycrystalline ke, amorphous ke, CRGS or CZTS, they have to be deposited on foreign substrate. And these substrates can be glass, it can be plastic, it can be fabric, but the whole idea is they cannot stand on their own. So they have to be supported mechanically by the substrate below, right? So the motivation is 150 to 200 fold reduction. If you talk about reducing the material from 200 micron to 1 micron, so that means we are actually reducing the material consumption by 200 fold. So maknanya kita jimat material lah. So for the same 200 micron, we might end up with a couple of solar cells already compared to one single cell of silicon. The efficiency for this technology is 10 to 15. So the materials are amorphous silicon, cadmium telluride, CIGS, copper, indium, gallium selenide. CZTS is copper, zinc, tin, sulfide solar cell for the second generation. So that's second generation. So let's go to the third gen, right? Third gen, remember the motivation is to reduce the cost but to increase the efficiency. In fact, to overcome the efficiency limit of the silicon solar cell, if possible, right? So these technologies include organic solar cell and perovskite solar cell. Yeah, I say so organic solar cell and perovskite solar cell. Organic is quite old already. Perovskite is new. It started back in 2009 and now it's only about 11 years or so. The film thickness is in fact thinner than the second generation. Walaupun dia masih lagi dalam kategori thin film technology, but then the film thickness is in fact can be lesser than the second generation. So in this case, it can be as thin as 300 nano to 500 nano. In fact, it can go up to 1 micron. So it only focuses on small market. Perovskite is a new technology with 24% record efficiency for single junction. This is 2019 latest record. Kita akan go through perovskite later on. I'm going to explain what is perovskite. However, the third generation, if you talk about these two technologies, this one and two, they are based on organic materials. So the similarities of this, one similarity is that they are based on organic material. Bila you guna organic material, this material is inherently less stable. So dia tak stable macam inorganic materials like crystalline silicon, ZATS, CRGS, amorphous. In fact, even though amorphous is not that stable, but organic is worse. Organic material is worse. So it suffers from stability problem and intensive research now. In fact, if you manage to fabricate, for example, perovskite solar cells, katalah you buat FYP hari ni on perovskite, and it's measuring around 15% efficiency, the next day you come into the lab, it might show up 2% efficiency. So due to degradation of the material within the solar cell. So that's how serious is the issue. Okay, so it has a lot of potential, but then quite a number of issues to address, particularly on the stability problem. Okay. Why is it not stable? Good question. Dia ada banyak root cause, Fazira. One of the root causes is the degradation of the organic material used in the absorber material. Maksudnya, if you go back to this page, alright, saya akan explain lagi. Perovskite ni it composed of MABX3, tapi since sudah tanya saya explain je lah. So MABX3, let me go through the whiteboard. I'm going to explain to you the details of perovskite. Oops, sorry. Whiteboard. Okay, can you see the whiteboard now? Nampak tak whiteboard? Can you see it now? Okay, good. Right. Perovskite ni is composed of MABX3. I'm going to show you later on. Lah, pakai color ni pula. MABX3 ni dia punya compound. So it's methyl ammonium lead. Dia pakai lead. Ni halide. We're going to go through later on. Let me write down. Ma is methyl. It's a bit of chemistry here. Methyl ammonium. Methyl ammonium. Nama penuh dia. B ni is typically metal. For example, lead or tin. X3 is the halide. Halide group mana? Halide. Still remember halide dalam periodic table? Group mana halide? Dulu kita belajar halida. Is it halida? Group mana? Halide. Remember? Trihalide. Dia 3 kan? X3. Trihalide. Yes, group 7, good. Yes, group 7, true. So X3 trihalide. So maksudnya it can be triiodide, triiodide, apa lagi? Tribromide, apa lagi? Trichloride. So it can be I3X itu boleh jadi I3, boleh jadi Br3, boleh jadi Cl3. Right? So it's methyl ammonium, lead or tin, triiodide, tribromide, trichloride. So sebab apa dia tak stable? Sebab methyl ammonium ni is the organic part. So this MaBX3 is actually a combination of organic and inorganic. So it's called hybrid solar cell. Hybrid organic, inorganic halide solar cell. So this part is actually methyl ammonium is the organic part, and this whole part is non-organic part. So methyl ammonium part ni dia tak stable, dia senang terurai, dia senang decompose. So bila dia terurai, dia dah tak jadi methyl ammonium lead triiodide, dia jadi something else, and that something else causes the change of the structure and therefore the degradation of the efficiency. Ada banyak lagi reason it's a metal migration dalam tu, and there are few more reasons yang still belum difahami oleh scientists at the moment. Okay. But one of possible root causes is the decomposition of the methyl ammonium. So scientists sekarang try to replace the methyl ammonium with some other molecules in order to retain the efficiency of the solar cell. Okay, sekarang you nampak balik slide kan? Right? Please confirm. Can you see the slide now? Oh no, really? Okay. Let me reshare. Okay, can you see it now? Okay, good. Right, so that's third generation organic and perovskite. Okay, third generation ni we're gonna go through later on. It's not yet in mass production yang besar, tapi kita dah ada a few companies starting up like Oxford PV, which is a spin-off from Oxford University. We also have Solid Technologies in Poland. We also have a couple of companies in China starting to mass produce perovskite solar cells. Okay, so let's look at the mass production of PV technologies. So currently, at the moment, we have 90% at least of first generation solar cells in the market. So maksudnya kalau you tengok 10 panel tu 9 based on monocrystalline and multicrystalline. Alright, and another 10% is based on thin film solar cells like cadmium telluride, CRGS, amorphous silicon and stuff. Right? And in fact, the market demand for crystalline silicon-based solar cells is getting stronger and stronger. So that's the main reason for that, and one of the main reasons is due to the plunging cost of the technology for crystalline silicon. Macam saya cakap tadi, back then 10 years ago, the technology cost for crystalline silicon was at $3 per watt. Now it's already down to 22 cents per watt. So original motivation to introduce second generation was to reduce the cost. Tapi bila sekarang, the reality is, bila cost of crystalline silicon dah reduced down to 20 plus cent per watt, sekarang ni second gen dengan first gen punya technology cost dah on par. In fact, crystalline silicon punya cost dah in fact a bit lower than the second generation. Tapi conversion efficiency of the first gen is like 18 to 25, while the second gen is 10 to 15 still. So why do customers opt for second generation? So that's why a couple of years ago banyak second generation technology yang went bankrupt. Okay, went bankrupt. Sebab tak boleh survive dengan penangan first generation yang dah murah. So if you divide this 90% punya cake ni of the crystalline silicon solar cell, you can see all this. If you look at 2018 annual production data, so they form this much of the PV in the market. So the top chunk belongs to the thin film, so mainly cadmium telluride from First Solar in Kulim and from the States and from Vietnam. But the rest of the 90% is made of crystalline silicon solar cells. So they are either mono or multi-crystalline silicon solar cells. But bottom line, they dominate about 90% of the worldwide market. Okay. So if you want to see the division of mono and multi from the 90% chunk, so as of 2018, you can see that multi makes slightly more than 50%, top here, and mono makes slightly less than 50%. So they are now, if you look into 2019 and 2020, and in fact the forecast for the future, mono will go higher than multi. Sebab mono and multi ni pun dia ada dia own competition dalam industri. Back then, a couple of years ago, like 7 years ago, multi was a lot cheaper than mono, tapi conversion of multi is slightly lower compared to mono. Tapi sekarang ni mono punya cost dah reduce banyak. So in fact, mono punya cost sekarang, if you compare mono versus multi, mono is only like 5 cent up to 10 cent per watt difference. So maksudnya kalau mono is 25 cent per watt, maybe multi is like 22 cent per watt, tapi the conversion efficiency of the mono is higher, and then the lifetime of the mono is higher as well. So sekarang multi pun susah nak fight dengan mono. So that's why if you look at the ITR PV roadmap forecast for the future, mono is going to go higher and higher. Multi is going to go lower and lower. Mono is going to go higher and higher. Okay. So this is the competition of mono and multi. If you look at production dalam industri, last year I went to visit our students in Jinko Solar. Many of the production lines in Jinko have been converted from multi to mono. So maksudnya dia punya multi punya product sudah phase out, dah tak ada dah. So now they are running only mono in Jinko Solar Pride. Okay, that's the power of mono over multi now, right? As of now. So, okay, we have discussed that crystalline silicon is a poor absorber, isn't it? So, if you compare with other semiconductor materials like cadmium telluride, so kalau kita compare dengan material yang other generation kan, so cadmium telluride, gallium arsenide, amorphous silicon, we know that silicon has a very poor absorber, this red line. And in fact, we also know that silicon is an indirect band gap material. And we also know that silicon has high reflection. Okay. Habis tu, kenapa silicon dominate more than 90% of the market? Kenapa silicon dominate more than 90%? Any ideas? Isn't crystalline silicon, bukan silicon, crystalline silicon, sebab amorphous kat sini, isn't crystalline silicon a poor light absorber? Then why does it dominate more than 90% of the world market? Being a poor absorber, more than 90%. I think as of now it's 93% or so. Okay, kenapa? So the reasons are on the next slide. So the source is abundant. So that's the first reason why crystalline silicon dominates more than 90%. Crystalline silicon is abundant in the earth crust, so in the form of silicon dioxide or SiO2. In fact, silicon is the second most abundant element in our earth crust after oxygen. Okay, so second reason is extensive knowledge from microelectronics industry. Microelectronics ni dah start lama, so chips industry yang kita guna dalam phone and tabs and laptops and cameras, so on and so forth, dalam consumer punya products. So knowledge, the physics, the background, the fundamentals from the silicon is well established. So maksudnya kalau kita nak start a new industry based on PV instead of crystalline, instead of microelectronics, they pretty much use the same knowledge, pretty much use the same equipment. In fact, the processes are a lot simpler than microelectronics. So maksudnya it's just a plug and play into a new business in comparison to starting up a completely new business like perovskite or organic or cadmium telluride or CRGS yang mana knowledge dia baru evolve quite recently. Okay, so in other words, in this point, this second point, the silicon has maturity compared to other technologies. Okay, second, the third reason is silicon has near ideal band gap. Even though the band gap is not ideal, or 1.4 electron volt, which is the peak of the solar conversion spectrum we're going to see later on, silicon is 1.1, which is not that bad for PV conversion process. Silicon is non-toxic if you compare with gallium arsenide and cadmium telluride, and in fact perovskite as well. They are all using toxic materials. So if you talk about cadmium telluride, cadmium is toxic and in fact cancerous, toxic. If you talk about gallium arsenide, arsenic is toxic. If you talk about what else, gallium arsenide, cadmium telluride, and perovskite. If you talk about perovskite, if they use lead is toxic as well. So that's why people are trying to replace the lead with tin. SN or tin yang tak toxic. Okay. If you talk about amorphous silicon, it's fine. If you talk about ZAT386, it's fine. Okay. So silicon is non-toxic. Silicon has high efficiency. As of now, it's about 26% efficient for the best cells in the market, and then the reducing technology cost. So it has now gone down to around 20+ cents per watt, so making it more appealing for the market. All right, if you want to talk about PV technology, there are rules that you have to use in order to decide which is the best solar cells for your design. So kat sini saya compare different semiconductor types. So we have silicon here with its band gap 1.1. So you can see here gallium arsenide, cadmium telluride is 1.4, 1.5. Cad sulfide is only a window layer because of the band gap of 2.3, 2.4. CRGS is somewhere 1.2, 1.3. Indium phosphide is similar. Germanium is too low, 0.7. So dia ada syarat. If you look at this is the solar cell conversion efficiency, theoretical conversion efficiency against the band gap. So this theoretical limit, kita panggil theoretical limit, is based on Shockley-Queisser limit. Shockley-Queisser limit. Shockley-Queisser limit, right? So any theoretical calculation. So it's based on the band gap. So this one says that if you want to have the highest conversion efficiency based on single junction, so the key is single junction, bukan multiple junction. Multiple you can go up to 40+, 50+, 60+. If you go for 6 junction, you can go in fact higher. So if you talk about single junction, it can go up to only about 31 to 32%. Gallium arsenide will be around 33%. Silicon is only about 29%. So 1.3, 1.4 is the peak conversion efficiency. So maksudnya theoretically, if you want to have the highest conversion efficiency possible, you need to use semiconductor band gap with around 1.4 to 1.5, which belongs to gallium arsenide, cadmium telluride, indium phosphide, around 1.3, 1.4. Silicon is a little bit lower, 1.1. So that's why it only end up with 29%. So if you go, so center is the peak. Okay, kalau you nak dapat maximum, you need to choose the center. If you go to the right, if you choose materials to the right, apa jadi? If you choose materials to the right, what's going to happen to the conversion efficiency? It's going to go lower. Why is going to go lower? Because if you go to higher bandgap materials, your solar cell will produce high VOC but low ISC. But the reduction of ISC is a lot more compared to the increase in VOC. So that's why kalau you plug in the equation, conversion efficiency equals to ISC times VOC times fill factor over Pin, like what we learned yesterday. So it's going to give you lower efficiency compared to the area in the peak in the central region. Okay, so it will give you higher VOC but lower ISC. Kenapa higher VOC? Any ideas? Kenapa higher VOC? Any idea? Saya pernah cakap tu dalam lecture when we talk about, I think, illuminated PN junction. If you can recall, I did talk about separation of your quasi Fermi level, right? QVOC max. QVOC max. So this is the band gap. If you have wider separation of your EC versus EV, or in fact your EG, you're going to end up with higher separation of QVOC max. So this QVOC max will actually translate into higher VOC in the solar cell, right? So that's why you get higher VOC but lower ISC in your solar cell. On the other hand, if you go to the left, you're going to end up with lower VOC but higher ISC. Why? So it makes sense. Kalau you punya separation of Fermi level ni, of QVOC ni akan rendah, maksudnya you punya VOC akan rendah. But why ISC is higher on the left and why ISC is lower on the right? Any idea kenapa ISC is lower on the right, ISC is higher on the left? For the left hand side, the reduction in VOC outweighs the increase in IC. So that's why you end up with lower conversion efficiency still if you compare to the central region. So any idea kenapa higher IC on the left, lower IC on the right? Can you relate back to the band gap photon energy? Tak lupa ke? Right, if you go to the right, look at the band gap now. The band gap is 2 point plus, right? 2 plus. So when your band gap is 2 point something, you need to have photons with enough energy equal to or higher than the EG, in this case 2 plus, to be able to knock out the valence electrons in order to be free for conduction. So maksudnya, the moment you go further and further to the right, you're gonna be left with lesser and lesser photons with the right amount of energy or more than the band gap energy that can knock out the valence electrons. So you makin ada sikit dan sikit photons yang available to knock out the free electron. So that's why you're gonna end up with lesser IC. So sebab photon yang incident tu dah kurang untuk produce free electron hole pairs. On the other hand, if you go to the left, you tengok dekat band gap sekarang apa jadi? Band gap dia kecil kan? So the EPH, the rule is EPH has to be more than or equal to the EG in order to knock out the electrons to be free. So kalau you go to the left hand side, the band gap is smaller, so you are left with many and many more photons which are available to knock out valence electrons from your semiconductor materials. So therefore, you can produce more and more electron hole pairs, and more will be collected, and more current will be generated from the solar cells. But the reduction in VOC will be a lot more, will be higher in magnitude in comparison to the increase in the IC. Therefore, the conversion efficiency will still be lower in comparison to the central region. Okay? Paham ke? So the central region is the best one, and silicon happens to be near to the central region, even though it's not the ideal case. Is it clear? Okay, ke? Paham? Good. Alright. So I'm going to go to another slide and then we're going to stop. Okay, so if you look at this is actually PV efficiency map or world record solar cell yang declared by all the scientists around the world, and it's actually let me zoom in full page. Okay, if you look at this chart is actually maintained by NREL in the States, Golden, Colorado. So you boleh tengok kat sini conversion efficiency on the y-axis and number of year on the x-axis. So you boleh tengok kat sini the legends show different types of solar technologies with the new world record. So kalau you tengok kat sini single crystal silicon, it's on this blue one, okay, saya mark kat sini. Single crystal monocrystalline without concentrator, so that means it doesn't use any concentration lens on top of the solar cells, so you can track the record of the single crystal solar cell ni yang kat sini ya. RCA, Sandia, UNSW ni tempat saya buat PhD dulu. They hold the world record for quite some time, 30 to 40 years I think. UNSW, all the way until this point, broken by one institute in Germany, if I'm not mistaken. Right, so you can also see other technologies as well. So you can see the multi-junction technologies in purple kat sini. Multi-junction with concentrator, without concentrator. It has gone up to around 47% for 6 junction. 6J here means 6 junction. 6 junction ni apa maksudnya? Maksudnya 1 PN junction, 2nd PN junction, 3rd PN junction, 4th PN junction, 6th PN junction. Yeah, all together 6 junctions. So you're going to have PN, 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 PN. So these PN junctions are going to be separated by one thin tunnel junction. Okay, so it's up to 47.1% now. So they are typically used for satellite applications, not for terrestrial application. So you can also see what else? Perovskite here, perovskite, organic, quantum dot. This one is all the 3rd generation technology. So the emerging technology, you can see perovskite, for example, the yellow color. Yellow color, where is it? Yeah, perovskite. Perovskite kat sini. Perovskite is quite new. You can see the curve. It goes up to around 25%, 24 to 25%, held by the one Korean institute, I think Creek in Korea. So it's quite new. Perovskite started in 2009 in the lab with efficiency of 3.8, and now in about 10 years it's gone up to 25%. So silicon has started, on the other hand, silicon has started back in 1954 with 6%. Sekarang baru 26%. So you can see the curve for silicon and the curve for perovskite. So the gradient is different, right? So the learning curve is different. So you can in fact see other stuff as well. Cadmium telluride, CIGS, amorphous silicon, what else? Single junction gallium arsenide. Gallium arsenide is kind of up to 29.1. As presented by some of you. Tengok kat sini mana gallium arsenide. Yeah, gallium arsenide is here, about 29.1, held by NREL or Alta devices in the States. Alright, so it's about 29%. Okay, you boleh tengok lah, thin film crystal, single crystal, silicon structure, banyak lagi teknologi ya. You can see from here. If you want to see this curve, you can actually visit NREL website, National Renewable Energy Laboratory, and then you just type PV efficiency world record or something. Then it will show you the PDF. Okay. So yeah, I think that's all for today. Do you have any questions for today's lecture? Ada soalan tak? How many more pages do we have? We're now on 27. Okay, I think we're gonna finish this chapter by tomorrow. Inshallah by tomorrow we're gonna finish, and then cuti raya kan? And there's no class next week. Cuti raya. Then after next week we're gonna come back with MOSFET. And then I'm gonna give you the presentation to assignment as well this week. I'll let you know on the website, WhatsApp and Elan. Right. Right. Any question for today? Is it clear so far? All right. That's good. There's gonna be some calculation as well, so I'll probably give you time to do yourself, and mungkin saya boleh bagi some question as well from the past year exam. Kita ada soalan on solar cell calculation and also from MOSFET calculation last few years. I can give you to try out later on. So tak ada soalan So if there are no questions, then yeah, that's it for today. I'll see you again tomorrow for our last class before Raya, inshallah. Right, Assalamualaikum, bye bye. Stay safe.